Okay, I'm going to do a quick review of what's in this slideshow, but I'm also going to do a quick review of a list of compounds you need to be able to draw Lewis structures for. And I want to try and make sure that we get to the point of why you have to be able to draw Lewis structures for the material that we're going into next. So, for the material that we're going into next, what we're going to be looking at is somewhat from the next slideshow after this, which is physical properties and bonding, and has to do with basically the overall shape of a molecule and how it can impact the attractive forces between them. And we predict the shape a molecule will be in by drawing its Lewis structure. I think the trickiest part of this is that Lewis structures are drawn flat on paper. And so a lot of times you don't realize what these molecules look like in 3 dimensions. So you may want to Google these as 3 dimensional models. If I can, before the next video, if I can find some that rotate and stuff, I'll show you what they look like. I may also have them linked to the slideshows because the next 3 slideshows are in a topic called intermolecular forces. That phrase should sound familiar. Inter means between. Molecular, specifically, we're talking about compounds that are covalent and the forces that are holding them together. Now, there's obviously forces holding other types of substances together. So, in that last slideshow, there's a very quick review basically of what are the forces that are holding ionic compounds together and what are the forces that are holding just plain metals together? Because they're 3 different types of force and they give each material different properties. Okay, so that's kind of the critical thing here is that the different types of attractive forces between particles, whether they're individual bonds between atoms or whether they're whole molecules, and you're explaining why do those molecules like to be close together or far away from each other, that explains on the larger scale their physical properties. So the part I figured you guys were going to be really confused about is either bonding electronegativity or drawing Lewis structures for atoms and molecules. So I'm going to run through electronegativity difference quickly. At this point, you should know what electronegativity is. If electronegativity is looking at how atoms attract electrons to themselves, if they have a high electronegativity, the highest number they can have is 4. They're very good at attracting electrons to themselves. And if they have low electronegativities, they're not very good at it. So, what happens between 2 atoms when they make a bond together, either in a compound or if they're making a molecule, they don't necessarily have to be in a compound. Let's review that quickly. Um, that determines that difference in electronegativity basically determines what are they going to do with their electrons when they make their bond. Are they going to transfer or are they going to share? And then once you figure out if they're sharing, how equally are they going to share? Okay, so there's a whole bunch of images in this slideshow to show you how electronegativity. I really don't like characterizing this as a conflict because remember, bonding is something all atoms want to do unless you're a noble gas, and it benefits them. So we have just noted that if you take two covalent, if you take a covalent bond between 2 nonmetals, and those people have similar electronegativities, they'll share very equally because they both have an equal amount of pull. But if they have very different electronegativities, you're going to see them sort of not sharing equally. Like the electrons are going to go kind of hang around with the person they think is cooler. Let's put it that way. And so they're going to share the electrons between them. The electrons will be between both atoms, but they're going to have a tendency to hang around the person with the higher electronegativity a little more often. So if you look up here, sorry, my stylus is not working, you guys. Um, so I'll do this with my finger and hopefully it won't be too messy. This weird little symbol up here, okay, this looks like this. This means partial. And the reason why there's a new symbol for a partial charge versus a whole charge is we're trying to help you to differentiate, tell the difference between when you're dealing with an ion and when you're dealing with a covalent structure where they're not going to make ions, but there is a certain amount of charginess, but it's not a full charge. They're not losing this electron to the other person. They just don't have it some of the time because the other person sort of hogs it. And so as a result, the person who's got the weaker electronegativity is going to pick up what we call a partial charge or a temporary charge. And so this is kind of a constantly fluctuating situation depending on where the electron is. But since electrons are very slippery and quick, um, what we find is that overall, even though they're sharing and they stay attached in a covalent bond, you're going to get this sort of partial positive charge on the person who has the lower electronegativity, particularly if it's a big difference in electronegativity. Like fluorine is pretty much like as high as you could go, and hydrogen is one of the lowest electronegativities of all the non-metals, right? Remember, the metals have really low electronegativities. If this was a metal, they pretty much would give up their electron, and this wouldn't be a covalent bond at all. All right, let's just clear this and go to the next slide. So this kind of competition almost between electronegativities, the difference between their electronegativities is going to determine what your bond type is. And so if you are looking at a question where it's hard to tell what they're going to do, because so like now we could give you a situation where there's a metalloid instead of a metal. We avoided that in the beginning because the only way for you to differentiate was to look if it was a metal and a non-metal, then it would be ionic. If it was two non-metals, it would be covalent. In this case, now we can be a little more fussy and we can deal with compounds that have more difficult differences. And that is because we now can look up their electronegativity numbers on table S and actually do the math. So one thing that you have to know is you have to memorize this range. There's no reference table that tells you if their electronegativity difference is bigger than 1.7, it'll be ionic. You have to know it. Okay, so this is the general range that they've been using lately. It has actually changed over the years, which I think is kind of funny, but it could be based on new research. It could also be based on the fact that it was confusing for students if they didn't make the ranges a little bit more clear cut. When I did this, it was like if you were under 0.2, you were nonpolar. If you were above 0.2, you were polar. And if you were above like 1.6, you were ionic. Like they had to shift the ranges a little bit because there are examples of covalent bonds where, like hydrogen and fluorine, where the electronegativity difference was really high. And my students would be like, oh, then it's ionic. And it's actually not ionic. A lot of it has to do with the fact that certain atoms, even if they are very weak compared to the person they're bonding with, they just simply won't give up their electrons because they're not metals. So, like hydrogen is pretty much a classic case of this. That doesn't mean that hydrogen can't occasionally have its poor electron ripped off. Fluorine will rip off an electron off of a hydrogen. But we just generally at this level of chemistry don't consider that to be an ionic bond. So we're going to create a range that allows you to look at that and be like, oh, it's still covalent. I don't know if that confused you more or less. Okay, so basically this range, you got to memorize it. And this range will tell you essentially if you do subtraction, whether you're dealing with, sorry, my alarm is going off, you guys, hold on. Okay, so what the only thing I'm going to remind you of right now before we go on to looking at some dot structures is you have to make sure that when you're reading a question, like a test question or a Regents question, that you know the difference between a bond between atoms and a force of attraction between particles. So between like molecules. So sometimes they'll talk to you about like the bond in a water molecule, like what's the difference between the electronegativities of the hydrogen and the oxygen in a water molecule. And then later on, what we're going to talk about is what is the force of attraction between whole water molecules that makes it want to be a liquid. Okay, so this is usually where the confusion comes in. And it could be partially because people don't read questions carefully. And I think partially it's just confusing. It's like we kind of keep using the same terminology, even though we're not talking about the same thing. We're kind of basically we're zooming in and zooming out. So if I'll show you that when we get into the other topics. All right, so let's skip ahead. I did show you in detail on these slides how to look up the electronegativity and do the subtraction, right? So this is an example of doing just the bond between one oxygen and one hydrogen in a water molecule and defining that bond as either polar or nonpolar covalent. Now you should already know it's a covalent bond because this is a molecular substance. It's made of all nonmetals. But now you have to basically be able to classify it as a polar covalent bond or a nonpolar covalent bond. So because this electronegativity difference is so high, it is a polar covalent bond. That just means that the two atoms, the oxygen and the hydrogen, are not sharing equally. They're not transferring electrons. It's not an ionic bond, but they're not sharing equally. And the reason why is because the electronegativity of oxygen is just really high. Oxygen, nitrogen, and fluorine have some of the highest electronegativities on the table. And so when they bond with people who have much lower electronegativities, they tend to be a little bit electron hogs, right? The electrons like to hang out with them more. They're more attracted to them. And so they tend to not share that equally, but they're still sharing. Okay. So here's our big next skill. You have to start thinking about where valence electrons are going based off of who they're bonding with and whether or not that's going to be a transfer, sharing, and then again, like unequal sharing or equal sharing. So what a Lewis dot diagram does, and this is named after a guy, it's named after a famous chemist named G.N. Lewis, who is really famous for creating this system for predicting what organic structures look like. And so I guess you could have called him an organic chemist, but he didn't do organic chemistry. He taught gen chemistry. He taught general chemistry for like his whole career. He really liked doing that. And he did a lot of his work in Berkeley, California. So they're Lewis dot diagrams. Lewis is the person who invented them. The dots represent the valence electrons. So this is why in the other slideshows, I was like, do you know the difference between total electrons and valence electrons? Because as we get closer and closer into really zooming in and looking at bonding, we have to be able to tell very quickly what valence electrons an atom has available to bond, because they're the bonding electrons. They're the ones they use to make bonds. So when we're drawing a structure to try and figure out how they're going to bond and how many bonds they're going to form, and roughly like how they'll put themselves together into a molecule, those are the electrons we're going to be looking at because that's what they use for bonding. So I remind you again on these slides that you have to be able to find the number of valence electron an atom has using your periodic table. So just as a reminder, you could go by their group number or you could go by the end of their electron configuration. Okay, we're going to be using a lot of main group elements for these, but you can get stuck with a transition metal. Just keep in mind that a metal-nonmetal bond is going to be an ionic bond anyway. So there's two main types of Lewis dot structures you have to be able to recognize and possibly draw. A lot of the multiple choice practice that you're going to see on the Microsoft forms is they give it to you in a multiple choice question. So you just have to be able to recognize it. They will, on a part 2, occasionally have you draw them. Now, I don't know how much they're going to be stressing this on future Regents exams, but for right now, it's still on the test. I think it's important to teach it to you because it is a big topic in college. So if you find yourself in a general chemistry class for college, you do need to be able to draw Lewis structures, and it's actually super easy. So let's go to those slides so I could show you how easy it is. First, you write the symbol for the element. By the symbol, I mean the letters that we use to represent that element. Chlorine is Cl, C is carbon. And then you draw dots to represent each valence electron. Okay, what you're going to do, traditionally, like the real way to do this is to put your first pair of electrons will always go on the top. But you distribute your electrons one at a time. And the reason for that is because in atomic theory, in modern atomic theory, what they realized is obviously electrons are negative and they don't like to be close to each other because they both have, if you put two electrons close to each other, they both have negative charges. So like charges like to push away. So they only pair up if they have to. And I mean, once they do pair up, actually they're very good at doing that, but they um, they essentially don't fill in unless they have to. They run out of room and they have to do it. So one of the ways to make sure you don't pair people who are not supposed to be paired is that you do one at a time and you go around in a circle. Okay. But we draw it like it's at the corners of a box. If I'm not mistaken, when Lewis originally did this, he was like I think he was a graduate student. He had built these like blocks out of paper, and he was using these blocks as a model for the electron locations in bonding. And so we still imagine this as being kind of a square and not a circle. And so think of it as the directions of like a compass, right? Like north, south, east, west. You're going to start at north with your first valence electron, and you're going to put one north, east, south, west, go around what we call clockwise, going in the same direction as a clock. So go to the right and then down and to the left and then up. Okay. And then once you run out of valence electrons, you're done. Okay. So if you have an atom, so this is why it's important to view these slideshows through on a computer. I'm pretty sure when you're looking at them on your phone, you can't actually see how I have the slides set up to show you what I'm doing. So watch, the slide is set up so that if I click on it, it shows you each dot as I'm putting it in place in order, right? So if I go to the periodic table, I look up carbon. Carbon's in group 14. So that means it has 4 valence electrons. Or I look at his electron configuration. His electron configuration is 2.4. He has 4 valence electrons, right? So doesn't matter how you do it, just make sure you're doing it correctly, like you know the actual amount of valence electrons. You start by putting a dot on the top, that's north, right? Then you go to the right, then you go to the bottom, and then you go to the left. At this point, I'm out of electrons. So this is the valence electron configuration for carbon. This is the Lewis dot structure for a carbon atom. Okay. In some books, it says to put the first 2 on the top. Here's why they have you draw it like this at your level. Because each time a carbon atom wants to make a bond, they need to make a bond by sharing another electron with the other person. So let me see if I can draw this as a picture for you. Let me just adjust the, oh, why can't I adjust the, oh yeah, there we go. All right. So essentially, a bond is a pair of electrons. It's 2. Each time you make a bond, you have 2 electrons in that bond, if you're making a covalent bond. Okay, so if you're making a covalent bond, you're going to borrow an electron from another person, and then you guys are going to share both of these electrons between you. So this would be the other person. Let's pretend it's a hydrogen atom. That's a very common thing, right? So carbon very commonly bonds with hydrogen. You've got these 2 electrons, the hydrogen sharing this electron with the carbon, right? And so essentially what carbon's doing is giving itself another electron in that location. So everywhere where there's a single electron is an opportunity to share a second electron with somebody and make a bond. Okay. If for some reason you're dealing with an atom that has 2 here already, in that location, they cannot make a bond. So if you were to draw this structure, like if I were to draw my Lewis structure and I did this, maybe like I'm like, okay, it's got 4 valence electrons. The problem with drawing it like this is it looks like people are already paired off. And that means that you can't tell if they can make a bond or not. Right now, it looks like this carbon can't make any bonds because how is he supposed to make room for somebody else's electron to share with them if he's already got 2 electrons in that spot? So it's really important that you draw it like this, 1 electron at a time, because what this diagram is actually showing you is that there's a space in each of these locations for carbon to make a bond. And so what this diagram tells you is that carbon can make 4 bonds. They can either bond with 4 different people, or they could make double bonds with 2 people. So we'll get into that later about like double bonds. But drawing these initial atoms or recognizing these initial atom structures is one of the first skills they're going to test you on. So it's actually really important that you be able to do this. All right, let's look at the other ones. So the ones I gave you in this slideshow are essentially the nonmetals and metals you're going to see most frequently. Now you could do this with pretty much any metal or any nonmetal, but especially in organic, which is what we're headed to next, you're going to see a lot of chlorine, a lot of oxygen, a lot of nitrogen, a lot of carbon, maybe some sulfur, a lot of hydrogen. So being able to do the Lewis structures for those guys very quickly is very beneficial. So if you click through this slide, it will show you. So I go to sodium. Sodium's group 1 valence electron. That's his Lewis dot structure. That's it. He just has 1 valence electron hanging out. Chlorine, group 17, 7 valence electrons. Now this is where it gets important that you put them in the right order. So I'm going to go 1, 2, 3, 4. Oh, I still have 3 more electrons to go. So I have to keep going. So now I'm allowed to make pairs. Okay, so now I'm going to pair them off. I'm going to put another one on the top. I have an X on that one to show you that this is my second electron that completes that pair. Okay, then I put one on the right again. Then I put one on the bottom again. And now I'm out of electrons. That's 7. So what this diagram shows you is that chlorine has 3 spots where they're already paired off. So that means that he can't make bonds in those 3 spots. He can only make a bond in one place. So this tells you immediately by looking at this diagram that chlorine can only make 1 bond with another atom. Okay, and the other ones are already paired off. These ones that are paired off already, they can't share them with other atoms in most cases. There's a little bit of an exception to that rule with nitrogen, but so these are known as unshared pairs because they're not going to be able to get shared in covalent bonds. So unshared pairs usually have to be drawn in diagrams. They're kind of important in terms of showing who's got a lot of electrons to throw around in an electronegativity battle kind of a thing. So chlorine's got 1 bond. It's going to be over here, right? All right, let's do oxygen. Oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. Okay, so oxygen will always have 2 unshared pairs and then 2 single electrons it can use to make bonds. So you can see immediately from this Lewis diagram that oxygen can make 2 bonds. Okay, so I put an X where a pair has already formed. That's just to remind you that you can't share electrons there. All right, so just don't forget you have two different kinds of bonding, and so you have two different kinds of Lewis structures. The Lewis structures are different for ionic compounds than they are for covalent compounds, and that is because you're showing a different thing happening. Okay, and so a lot of people get confused about this too. And then they show me a structure for an ionic compound that isn't possible. Okay, ionic compounds don't involve sharing electrons. So if that's the case, you can't show them in the picture sharing. In covalent compounds, they are sharing. So you're going to show them sharing by drawing the structure differently. So first things first, I'm going to show you what an ionic structure looks like. In an ionic structure, they're not sharing. And so we don't show them connected with lines or with dots for electrons between them because that would imply they were sharing their electrons with each other. And they're not. Okay. Chlorine, who has the higher electronegativity, is going to take an electron from sodium. Sodium, who has a low electronegativity and would really like to get rid of an electron. Remember, this is not that they're not being mean to each other here. Sodium really wants to have a noble gas configuration. Remember, that means having an octet, 8 electrons in your outermost energy level. Sodium's electron configuration is 2-8-1, meaning that if you want to have 8 in your outermost, if you could just get rid of that 1 on the outside, that would be fantastic. It just so happens that chlorine has 7, and in order to get 8, he needs somebody to either loan him 1 and share it or give him 1, right? So that's fantastic. So sodium gives an electron to chlorine. Both of them get a stable outermost electron configuration, and they're happy like that. As a result, though, of their electrons being lost and gained, they're no longer neutral atoms. When sodium loses an electron, it picks up a positive charge. When chlorine gains that extra electron, it picks up a -1 charge. Okay, so because this was a transfer, somebody gave an electron to the other person, we don't show them connected because they're not connected, they're not sharing. What's holding them together is now they got charges. So charges make people attracted to each other. So they're hanging around together because they're attracted to each other like magnets. Okay. And so when you show a Lewis structure like this, you show a finalized structure that shows that the transfer has already happened. Then you draw brackets around them. Did you see those brackets? The brackets are to show that they're not actually sharing, they're not connected. And then you give them the charges that are associated with them based off of who lost it, who gained. Okay, so this is why it's really important that you go back and do your bonding review. So after this transfer happens, this is, again, I have an X on this electron. This time I'm doing it to show you that that electron was not chlorine's. It was sodium's. Sodium gave it to chlorine. Okay, they were very happy about that situation. After the transfer, I put brackets and charges to show that this has caused them to gain a charge and that they are not connected. They are sticking together, they're making a bond, but they're not connected in the same way a covalent bond makes you connected. So this is why, and I've gone over this a bunch of times, ionic compounds don't make molecules. Okay? Molecules are units where everybody stays connected because they're sharing their electrons. In an ionic compound, that's not how it happens. Okay, they don't do that. They form like a continuous chain of people who are attracted to each other after electron transfer. Okay, now a little bit of background on the bracket thing. You have two options for brackets. You can either draw brackets around everybody, both sodium and chlorine, and then you show the charges technically outside the brackets. Okay, or you could just draw the brackets around the person who got to be negative. But you got to draw brackets at least around the negative ion. So sometimes what I say is just draw brackets around everybody so you can't forget. All right, now it gets a little bit trickier when you're dealing with people so this one's like a 2 electron transfer. So barium is a group 2 metal, like magnesium or calcium. They have barium atoms. She's got 2 electrons that she's willing to give up. And oxygen needs 2, right? If you think about oxygen picks up a -2 charge, it's in group 16. He has 6 valence electrons, so he's going to want 2 electrons. So one option, if it's available, is that he could bond with somebody who has to give up 2 electrons. So again, this is beneficial for both people. When barium gives up 2 electrons, they transfer to the oxygen. Barium picks up a +2 charge, oxygen picks up a -2 charge, and then they balance each other out. This is what we were doing when we were charge balancing in ionic compounds when we were writing formulas, is we were showing this happening. Okay, and then when you're drawing a Lewis structure, you're showing the charge as well as the electrons that moved from one person to another. Okay, it's really important that you understand that the bottom one here is the final structure. What I'm showing you in the first 2 steps is the process of this happening so that you could figure it out while you're drawing structures. Okay, now even more confusing option here is what if you happen to be able to give up 2 electrons, but the people who are available to bond with, they can only take 1. If that happens, then what you'll do is you'll just give 1 to 1 chlorine, and then you still have another electron, so you could give another one to another chlorine. And this is how you get a cation bonding with 2 anions. Okay, so chlorine's going to end up, you're going to end up with 2 chlorines being attracted to 1 calcium because the electron transfer allowed calcium to give 2 different chlorine atoms their 2 electrons. Okay, now there's 2 ways you could write this. You could draw the whole thing out, like you could show. So again, this over here, let me just circle this. If you're doing this on a test, this is my work. This is my final answer. Now, if you want this to be a little easier and less drawing, you could also say it like this. You could say this calcium is bonded to 2 chlorines. Okay, but it's not, it's almost like a coefficient. You just put a big 2 in front of it. So you could either draw 2, or you could say, there's 2 here, but I'm not going to draw them. Okay, so there's kind of like a slightly lazier way to do this if you want to do it that way. And you really have to practice this, otherwise you're not going to be able to do it by yourself on a test or a quiz. Okay, if the ionic compound has more than one type of atom, you're going to either draw 2 ions or put a coefficient in front of the one that you have more than one of. So here I wanted you to do this, a very similar example. Again, this is a group 2 metal bonding with a halogen that can only take 1 electron. So again, you've got a magnesium. Magnesium has 2 valence electrons available, but a bromine can only take 1. So magnesium is just going to give 1 to 1 bromine and 1 to a different bromine. So that allows that magnesium ion to bond with 2 bromines. But again, this one on the right, so this is my work, this is my final answer. In your final answer, you must make sure you show all of these things. The charge they've picked up, the electrons that were transferred have to be with the person they were transferred to. So now you don't have to put that X on the electron that bromine got from magnesium. I'm doing that so that it's easier for you to visually see where it went. Okay, but you have to show that bromine has an octet now. He has all 8 that he wanted. He got it from the magnesium. And then you're going to make sure the negative one goes in a bracket, or you could put both of them in brackets, and everybody has their charge. All right, now it's different for covalent structures. Okay, covalent structures are shown one of 2 ways. On the left, in this one, you have electrons going around, and you're showing the pairs. Okay, this pair that I'm showing, one of these electrons belongs to nitrogen, and one of these electrons belongs to hydrogen. Okay, this is an unshared pair. That means that that one paired off already when you did the Lewis structure, and it's not available. That's not an available bonding site. Okay, so same thing with oxygen. When we did the Lewis structure for oxygen, you could see that it had two places where they were already paired off, and so they couldn't make bonds there. Okay, and then the other two spots where he had a single electron, he could share an electron with hydrogen. So this is like coming to a party and making sure you bring something with you. Oxygen brought one electron to the party, hydrogen brings an electron to the party, and together they share. Okay, I'm going to point out to you that this structure is technically incorrect, but it is valid to show it this way. One of the things that's going to happen though is that you really should show the structure for water like this. And this we're going to go into this a lot more later on. This is what's known as a Vesper structure, and I'll get into that what that means later. But essentially, what it's showing you is the actual shape of a water molecule, and it's shown that way by getting the unshared pairs to all be in one spot, and the people who are actually bonding and sharing are down at the bottom. That is why this is a bent structure. Okay, now there are some steps here to help you draw Lewis diagrams for covalent structures that will prevent you from making mistakes. Okay, so the first step is always draw everybody separately. You want to draw the carbon, draw the oxygen, draw the hydrogen separately so that you can scope out how many places each one of them can make a bond. You have to consider that they have limitations to how many atoms they can bond with. And there's a little trick that we use to remember this. It's called HUNK 1, 2, 3, 4. And that stands for hydrogen can make one bond, oxygen can make two bonds, HUNK, hydrogen one, oxygen two, nitrogen can make three, and carbon can make four. Now you should be able to see that by drawing the Lewis structure for each atom, but this is just a quick way to remind you if you're checking your drawing to see if it's right. Did you give somebody too many electrons? Because you can't just draw a structure and just start putting dots everywhere. They have limits to what they can do, and you can't give everybody electrons that they don't have. And then usually, and it's not always true, but usually, so like the very first exception is water. Water is always written H2O, but the hydrogen's not the atom in the middle. And the reason why is because hydrogen can only make one bond. So if you put him in the middle, you're implying that he can put like two other people on the sides of him. He can't do that. He's too little. Okay. But in a lot of other compounds, usually the atom that comes first, like if it's carbon, she can make four bonds. She's going to be in the middle. Okay. And that means everyone else is attached to her. She's the center of the molecule. Okay. So we're going to draw three really common structures. And again, if you're going through this slideshow on a computer, you're going to be able to actually click through and see how I get this to all line up. Okay. So first thing I'm going to do is I'm going to show you the Lewis dot diagrams for each individual atom. So that shows you right here, right? Oxygen again has two bonding sites. Hydrogen only has one. Nitrogen has these three spots it can bond, but up here where this unshared pair is, you can't make a bond there. And carbon has four individual electrons, so carbon can make four bonds. Now water, NH3, NH3, please keep in mind, has two different, well, they all have more than one name. In the molecular naming, you already know this is nitrogen trihydride. The common name of this molecule is ammonia. It is a molecule, I'm giving you the molecules we use the most. So these are like the ones they're most likely going to ask you about. And so memorizing them and knowing them well is worth your time. Okay, and then the last one you should recognize, CH4 in regular molecular nomenclature is carbon, tetra means four, carbon tetrahydride. Okay, now ammonia is a common name. So if somebody asks you for their IUPAC name, that's their formal name in the chemical nomenclature system. You are going to say nitrogen trihydride. Ammonia is a common name, which means it doesn't tell you how much nitrogen and hydrogen is in that molecule. So it's not that helpful. Again, carbon tetrahydride is a IUPAC name for a molecule, When we get to organic nomenclature, though, which we're going to do soon, that's the naming of organic molecules. That's what nomenclature means. We're going to go with the name methane. Okay, methane is a real IUPAC chemical name. It's just a different naming. It's a different set of rules for organic molecules. Methane is natural gas. We've talked about methane a lot. So definitely you should know methane. You're going to need to really know its structure very well. Right? So here's me. I draw out, I say, okay, the formula is NH3. I draw out all three atoms and I start to think about where are these hydrogens going to go based off where they can pair off with an available electron that can bond on this nitrogen. And so I created these graphics where I show the pictures overlapping so I can show you where these hydrogens will go to make this structure. Okay, so you're going to see it drawn like this, where each of these two dots represents a bond between the nitrogen and the hydrogen, and this unshared pair at the top is not. Okay, now it can also be shown with a line. Each line represents these two electrons. Okay, so one line drawn between two atoms represents two electrons being shared. Here is methane. So I draw all the atoms. I say, okay, the formula is C with four H's, right? So I've got a carbon and four hydrogens. I'm going to go ahead and look at who's got a bonding electron available. And I'm going to put a hydrogen in each spot on this carbon where there is a spot available to make a bond. And that shows me the structure for this molecule. Okay, and here is our one of our best friends in the whole world, water, right? So I look at the bonding structure for just oxygen. I say, okay, oxygen's got two spots where she could go ahead and bond with somebody. And so a hydrogen's going to go in each of these available spots. Now you're going to notice that when you're drawing a Lewis structure for a single atom, if you do it the way I taught you, where you go around in a circle until you don't pair people until you have to, you're going to make it so that the shape of the molecule is correct when you put the atoms in their places, because that is the correct shape for a water molecule. It shouldn't be in a straight line. Water molecules, that would be called a linear molecule. Linear means line. This is not a linear molecule, okay? It looks like this. So these are two different ways that you're going to see these represented on paper. You could either show two dots to represent the bond, or you could show one line to represent the bond. So if you're new to this, I usually kind of say you could do this on training wheels, and you could draw the dot and the line. And that would just be a reminder that this bond has two electrons in it, because they like to ask you questions like that on a multiple choice question. So I could even do this. This is a legal move. Carbon can do this. Carbon can also do this. Each of these lines represents a bond where two electrons are being shared. So like this carbon is sharing four electrons, two in this bond and two in this bond. This pairing, this bond is sharing two. It's a single bond. A triple bond, they're sharing six, two here, two here, two here. So all you have to know is that a line represents the sharing of two electrons. If you have more than one line, they're sharing more than that. It's a pair for every line. Okay, so I show you for each one of these. It's really important that you start to recognize like the line structure as well as the dot structure, because they very frequently flip back and forth. They mean the same thing, they're just different ways to draw it. Okay, so this is a line structure for ammonia or nitrogen trihydride, where instead of pairs of electrons, I showed you a line for the two electrons. Okay, and again, drawing it like this gets you closer to showing the actual shape of how this molecule looks in real life. Okay, so here is a list of structures you really need to learn how to draw. So I'm going to go over those in more detail, either in another video or in person. Okay, now here is where in the slideshow it starts review material. It is incredibly important at this point. If you don't know the difference between an ionic and covalent compound, if you can't write a formula, if you can't balance an ionic formula, if you're still writing formulas incorrectly, you are way behind. And if you think you're lost, you're definitely lost, because at this point you should know all that stuff. Now, the problem really is that there's no way to unbury yourself unless you go back to the old material and learn it. So it's Thursday, you've got a break in one more day. You're going to be off for 9 days. I know it's a vacation, but if you're behind, you have work to do. Okay, so if I'm back, and I'm going to be frank with you guys, I'm a workaholic. I was raised as a workaholic. If something happens to my mom, I'm going to be back. I'm probably not going to take too much more time off because working keeps me sane, and it's going to help me be distracted from, everything we're going through. So I'm going to be working. In fact, I'm going to be working more than I was working before. So you can expect me not to like take some time off, but to turn it up. I'm going to kick it up a notch. So I will be extra when I get back. I will not be low key. So dead ass, if you don't know what you're doing over the break, you better catch up. Please don't forget also that on the YouTube channel, there are also videos for naming. That background material is vital at this point. If you can't work with compounds, if you can't write equations, the rest of this is really not going to make any sense to you. So please, please, please get comfortable with it. Also, don't forget in the drive itself, if you go to the full drive on the work plan, or if you just Google it, you can get to a full copy of the New York State reference tables. So you'll have table S in front of you. You'll have a periodic table that has all the charges and the electron configurations. So it's in my drive. It's also it's also just openly available on the internet. The New York State Regents website I'll just show you really quick. They did this annoying thing where they like buried things behind links. So like if you want to Google it and you just put in New York State chemistry reference tables, they make it stupid, and you go to click on it and it leads you to like another page, and then you have to like sort out what you need to click on. So you're going to click on this link. It's going to take you to a PDF doc of it. Okay, so you do have to be able to open PDF docs, but most computers and phones can do that. You can zoom in with these buttons up here, and then when you get down to those big tables like the periodic table and table S, you're going to need to rotate it. So see this button over here? If you're on a PC or an iPad, you can rotate. Now, this is a PDF doc, so you can also download this if you want to have it in your phone. Look, if you want to be a good chemist, if you want to be a good chemistry student, you should want to have your periodic table with you, like all the time. And if you have a printer at home, I don't recommend that you print this whole document, but you can also just select pages. So the reference table is, John, I have this reference table practically memorized. The reference table is about 12 pages long. So if I if I went to page 10, it'll preview which document you're on. So page 9 is the periodic table. You can just print that. So the settings are go to custom and just type in the number of the page you want to print. So if you're home and you're like, your mom's going to flip out because you're using too much toner, you don't have to print all 12 pages of the reference table. Just print the pages you need. Like if you want to just print the periodic table and table S, do that. Okay. All right. I'm going to sign out for now. Uh, thank you, you guys, for being so understanding and all your support. And I don't know when I'll see you, but I'll see you when I see you.